keep it.
Okay, is my screen visible to you?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, let us start with attendance. Please answer your attendance. Aditya Kumar,
Yes, sir.
Anand,
Yes, sir.
Anand Kumar,
Yes, sir.
Arunachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Keshav Prasad,
Yes, sir.
Lakshmi Narayanan,
Sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Roshan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Vallish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijay
Present, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj,
Present, sir.
Okay, welcome back to this course on IC engine combustion and pollution. I have concluded chapter 1 in the previous class and provided an overview of contents that we are going to discuss in chapter 2. So these are the contents that we are going to discuss in chapter 2. Chapter 2 deals with combustion, actual combustion process in SI and CI engines. And before we move on and discuss the actual combustion process, we are going to discuss about thermodynamic aspects of combustion. And these are the contents that we discuss under this topic. Okay, so I will start with a brief overview of why we need to study thermodynamics of combustion, what are the complexities in actual combustion process, and what kind of information we can get by applying thermodynamic principles. So then we will discuss about this stoichiometry, combustion stoichiometry, which provides you the composition of the combustion products. Then I will discuss about application of first law of thermodynamics to study combustion. By applying first law of thermodynamics, you will be able to get an estimate of energy released during combustion and also the maximum temperature reached by the combustion products. So these two useful information we can get by applying first law of thermodynamics. Then I will talk about second law of thermodynamics to study the combustion event. So here I will introduce chemical equilibrium concept, which is very useful to get the composition of combustion products. If the number of combustion products are more, the stoichiometric principle alone is not sufficient. So we will apply second law of thermodynamics and use equilibrium, chemical equilibrium concept to get an estimate of composition of the combustion products. So we need to track composition of the combustion product because, as you know, some of the products are pollutants, objectionable pollutants. So we need to know about the composition, okay, product composition. That's the idea here. I will close this chapter with a brief discussion on chemical kinetics. So thermodynamic principle provides only steady state approximation of combustion process. Transient information can be obtained only by applying chemical kinetics. Okay, so I will briefly discuss about chemical kinetics and I'll also talk about what kind of information, transient information you can get by applying this chemical kinetic principle. To start with, we are going to first see about why we need to discuss thermodynamic aspects of combustion. So combustion process, internal combustion engine process is a complex process. IC engine combustion here refers to both SI and CI engine combustion. Is as such, it's very complex because of the reason that it occurs rapidly at high temperatures. The temperatures we are talking here are well above 2000 Kelvin during combustion event, and the time scale involved is so low. That's why it's a very rapid process and happens at high temperature. That's why we don't have analytical capability to completely resolve. Even today, we don't completely understood the combustion process. Okay, so we can say that the combustion process in IC engines are not well understood even today, primarily because of the reason that it happens at high temperature and it happens at a very small time scale. Okay, so it's very difficult to capture what is happening during combustion even with any instrument that we have today available today. Any instrument, combustion instrument, it's very difficult to capture this event, combustion event precisely because of this reason. Also, it involves several physical and chemical process. Okay, it involves complex coupling of physical and chemical process. So as I said, the process occurs rapidly. What is the time scale we are talking? You know, engine cycle time itself is very low, and engine cycle time is a function of engine running speed. So the time required for completing one engine operating cycle is inversely proportional to engine running speed. When engine running speed is high, the time required to complete a cycle will be less. Higher the engine running speed, lower will be the time scale. So this is a time required for one cycle, and combustion process, the duration of combustion is a fraction of the total engine cycle time. So we have a cycle time, generally it's around millisecond time scale, and combustion event is one of the event during the entire engine cycle. So it's a fraction, it occurs during the fraction of a engine total cycle time. So that is, so generally this time scale will be around microsecond or nanosecond. So very small time scale is taken to complete the combustion event. So this is one reason, and second one, as I said, the temperature involved is well above 2000 Kelvin during the combustion event, both in SI engine and CI engine. So it's a combination of very small time scale and very high temperature. That's why we don't have an instrument. Okay, the limitation of the current instrument is it's very difficult to capture this event because of this combination of very high temperature and very small time scale. So still it's not completely understood. Okay, this is one of the complexity of this process. And this process involves coupling of physical and chemical process. I'll briefly talk about what physical and chemical processes are involved in SI and CI engine combustion. And during combustion event, this physical and chemical process are coupled, meaning we cannot separate these two, they are interlinked. Okay, let us briefly look at how SI engine combustion is happening. And then let us see how this coupling of physical and chemical process are happening. So in a spark ignited engine combustion, as we have discussed earlier, we have a spark plug. We discharge electric spark to initiate the combustion event. So when you discharge electric spark, you are going to discharge it within this two electrode. Within the two electrode, you have a very small gap, less than 1 mm gap. Okay, less than 1 mm gap you have between these two electrode, and you are discharging high voltage between these two electrode. And what you have within this two electrode, you have a fuel air mixture. Within the ignitable range, you have fuel air mixture that is contained in this electrode gap. Once you discharge this electric spark, a flame will get formed here, and we need to form a stable flame. Otherwise, the combustion cannot sustain. Okay, so you are discharging spark to initiate combustion. When the combustion event has to sustain, this flame that is formed around the spark plug region has to be a stable flame. So we are actually forming a stable flame around this region by discharging electric spark. And then this flame, as you could see here, moves across the combustion chamber. This is an optical engine image of the combustion event. We are tracking how the flame is moving at different crank angle, 3 degree, 4, 6 and 8 degree. ATDC is after top dead center. TDC is a reference point. I will talk more about this reference point later on in detail in the combustion topic. Okay. So here we are seeing how the flame is moving across the combustion chamber at different time. Time is presented in terms of crank angle. So overall combustion event in a spark ignited engine is a flame propagation based event. That is what we are seeing here. And this flame movement will enable burning the mixture that resides in the combustion chamber. What do you have in the combustion chamber? Unburned fuel air mixture. The flame is moving across the combustion chamber and igniting unburned fuel air mixture. Okay, that is how the combustion event is proceeding. Energy release is happening in a typical spark ignited engine. And this energy release is what we are converting into work in the engine, which is an energy conversion device. So overall combustion event here is a flame propagation based event, and this flame movement is dependent on both physical process and chemical process. And these two processes are coupled, interlinked. We cannot separate them. Okay, so now I will briefly discuss about these processes involved. So overall SI engine combustion, it's a flame propagation base. A flame is moving across the combustion chamber. In fact, it forms two regions in the combustion chamber. One is burnt gas region, which is behind the flame front, and the other one is an unburned mixture region, which is ahead of the flame front. So this is how the flame moves. Ahead of the flame front, you have unburned fuel air mixture, and behind the flame front, you have burned gases. So there are two regimes formed in the combustion chamber because of the flame movement, and the flame has to move and ignite this mixture. I already said about normal combustion and abnormal combustion in SI engine. Abnormal or knocking combustion happens when this mixture start to self-ignite. If there is any self-ignition of unburned mixture, there is a knocking combustion, which is going to damage the engine in the worst case scenario. This is what we discussed in chapter 1 when we discuss about antenna quality of fuel. This is one of the important fuel quality requirement, antenna quality. This mixture, unburned mixture, has to resist self-ignition. And at any point of time, the flame has to ignite the mixture. This is a normal combustion. Okay, so we are talking about how the flame moves inside the combustion chamber, and this flame movement is governed by both physical process and chemical process. What are the physical process involved? One is heat transfer. The flame will radiate heat. There are different modes of heat transfer. You know, the predominant mode in during the combustion event is radiation. The flame is going to radiate heat to the unburned mixture from the burn zone to the unburned zone. Convective heat transfer also take place, but radiative heat transfer is predominant here. So there is a heat transfer, which is a physical process from the burned region to the unburned region. So unburned mixture temperature will rise because of the heat transfer. Then there is a mass diffusion. Mass diffusion happens between unburned and burned mixture due to concentration gradient. So there is a concentration gradient between the two regions that will allow mass transfer to happen between the two regions, which is a physical process. Then there is a fluid dynamics. Fluid dynamics refers to how you are creating fluid motion inside the combustion chamber based on the design of the combustion chamber. In the end of the chapter, I am going to show you the typical design, combustion chamber design. This is one of the important, this plays a significant role in this flame movement. You need to create appreciable fluid motion inside the combustion chamber to increase the flame velocity. So these are the physical processes that are happening during the flame movement. Heat transfer, mass diffusion, and the fluid motion happens based on how you design the combustion chamber. There are also chemical processes that are happening simultaneously. And this chemical process, as you know, it is governed by the chemical kinetic scheme based on the molecular composition of the fuel, which we have discussed in chapter 1. Gasoline and diesel are complex hydrocarbon mixture, multi-component mixture. And each hydrocarbon has a characteristic chemical reaction pathway. Characteristic chemical reaction pathway, meaning that it will get involved in a chemical reaction. It get involved with a particular reaction scheme. I'll briefly talk about this kinetic in the end of the chapter. But here, just take a note that the overall energy release that what you are seeing in during the combustion event is a resultant of energy release from the individual hydrocarbon. Each of them has a characteristic reaction pathway. So there is a chemical process governed by kinetics, and this is based on the molecular composition of the fuel. Okay, and I said these two processes are coupled, meaning they are interlinked. For example, the way the heat transfer is happening is going to affect the rate at which the chemical reaction take place. You know, the chemical reaction rate is highly sensitive to the temperature. When the temperature is increased, kinetic rate is going to get increased. And the temperature rise is primarily due to heat transfer from the flame zone to the unburned mixture. So this physical process is in fact affecting the chemical process. Okay, and vice versa. The rate at which the chemical reactions are happening is going to affect the thermal energy release, that is going to affect the heat transfer that is happening in the combustion chamber. This is what I say, these two processes are coupled. They are interlinked. Okay, there is a physical and there is a chemical process, and these two are coupled, and the overall flame movement in the combustion chamber is because of both the process, physical and chemical. So this is how the SI engine combustion event is happening. I'm going to discuss more about this later on. Now we are looking at why we are studying thermodynamic aspects of combustion. What is the complexity in the actual combustion event? This is what we are looking at now. So when you look at CI engine combustion, so as we have earlier discussed, when we discuss about the role of fuel, we know that in the CI engine, we are spraying fuel at a very high pressure, and this fuel is sprayed near the end of compression stroke. And what do you have inside the cylinder when you spray the fuel? You have air. What is the condition of air? It's a higher pressure, higher temperature based on the compression ratio. Typically, it is 30 bar and 700 Kelvin, okay, which is going to change based on the compression ratio of the engine. So you have air residing in the cylinder at high pressure and high temperature, and you are spraying fuel at a very high pressure into this air, right? And after this, you have a sequence of processes that happens one after other. There are physical processes involved and there are chemical processes involved. Okay, so what are those physical and chemical processes? So here are they. The physical process that takes place as soon as you spray the fuel, one is the spray with a finite profile, and the spray will move inside the combustion chamber against the air resistance. This is what I mean by spray momentum. So the spray will move inside the combustion chamber with some velocity, right, governed by the injection pressure as well as the air resistance. Then you have air entrainment. Air is moving inside the spray profile, okay, inside the spray cone region, and because of air movement, you are actually vaporizing the liquid phase fuel. And then you have vaporization, which is a subsequent process. And once this happens, there is a mixing, fuel air mixing, and you create a ignitable mixture through this physical process, and you are rising this ignitable mixture to the ignition temperature. So combustion can happen only if you have ignitable mixture, only if the ignition temperature is available. If either of this is missing, there is no combustion at all. So after you spray the fuel, this is the physical process that happens in the CI engine. You are creating an ignitable mixture and you are rising that ignitable mixture to ignition temperature. Then there is an associated chemical process which involves radical formation, as I have said in the first chapter. So this is governed by kinetics, chemical kinetics, based on the molecular composition of the fuel. Okay, again, here we have a complex multi-component fuel. Diesel fuel is complex multi-component mixture, and each hydrocarbon has a characteristic chemical reaction pathway. And so overall, this combustion event in a CI engine is referred to as mixing control combustion event, because as you know, until otherwise you have created this ignitable mixture, there is no combustion at all. That's why mixing, fuel air mixing carries a significant role in CI engine combustion. That's why it is referred to as mixing control combustion event. Okay, so once you have this, you have this chemical kinetics taking place, and these two are coupled, as you could see. Because of the chemical kinetics, thermal energy is released. When thermal energy is released, you have higher temperature inside the cylinder that will improve the physical process, meaning the mixing. You have a liquid phase fuel that should get into gas phase through absorption of latent heat, and then it has to mix with air within a finitable range, which is what is the ignitable range. So this thermal energy release during the chemical process is helping in the physical process. Okay, until otherwise you have an ignitable mixture, there is no chemical reaction at all. Okay, chemical kinetics cannot get started until you have a ignitable mixture. Thus, you can see that these two processes are interlinked, right? Coupled, interlinked, and because of that, the combustion event is happening in a CI engine. So overall combustion event in a CI engine is a mixing control combustion, and in SI engine it's a flame propagation based combustion. Nevertheless, both the event happens at very high temperature with a very small time scale. So it's a combination of small time scale, very high temperature. This is the complexity of IC engine combustion process. So considering this complexity, we are starting with the simplified thermodynamic based approach. Okay, so this approach simplifies the analysis of combustion because, as you know, thermodynamic approach involves equilibrium based approach, and this is applied to a state of a working fluid. State, when I say state is a collection of properties. Okay, state is a collection of property and it exists in an equilibrium state. So when I say that I am going to do a thermodynamic analysis of the combustion process, what I mean here is I am going to consider equilibrium based approach. I am going to consider the state of the working fluid before the combustion event and after the combustion event. What is happening during the combustion event is highly transient, right? Thermodynamic cannot pitch in there. But what we do here, we are focusing on the state of the working fluid before combustion and after combustion, right? Why do we do that? What kind of information, useful information you can get by doing this thermodynamic analysis? So this analysis, thermodynamic analysis, provides some vital important information about the combustion event. Those are presented here. It provides you information about the properties of working fluid before combustion and after combustion. It provides you an estimate about how much of energy is released during the combustion event, and this is done by applying first law of thermodynamics. By applying first law of thermodynamics, you can get an estimate of how much of the thermal energy is released because of the combustion event. Again, this is one of the important information that we need to have. The second useful information you can get is the maximum temperature reached by the combustion product. So when thermal energy is released during combustion, it appears as a heating effect. What do you mean by heating effect? It will appear in the rise in temperature of the product. So initially you have reactant. What are the reactant? Fuel and air. Fuel and air combust and it forms product. The thermal energy released during combustion appears as a heating effect in the sense that the product temperature is going to rise based on the quantity or magnitude of the thermal energy that is released. Higher the thermal energy release, higher will be the product temperature. Lower the thermal energy release, lower will be the product temperature. So by applying thermodynamic principle, what you will get is the theoretical maximum temperature reached by the combustion product. This is one of the important information you need to have when you do combustion analysis. The maximum temperature reached by the combustion product can be estimated by applying first law of thermodynamics. This is one of the useful information. So when you design a combustion system, you need to know about what will be the maximum temperature reached by the combustion system, because that will help you to fix the materials for the design. And in fact, one of the fundamental, I would say, fundamental data you need to know when you design a combustion system is how much is the maximum temperature. Okay, this is a vital information you need to know to fix the material and the chamber design. And this is what is going to decide the durability or life of your combustion system. So you need to know what is the maximum temperature reach. From a design perspective, this is a vital fundamental information you need to know. Also, this maximum temperature is going to affect the products. Some of the combustion products are pollutants. Later on, we are going to see how the temperature affect the pollutant formation. But this temperature information is also useful to get an estimate of the products, combustion products. Some of them are pollutants. So this product information can be indirectly obtained by knowing the maximum temperature reached by the combustion system. So this maximum temperature can be obtained by the thermodynamic analysis. The other useful information you can get is the composition of the combustion product. Some of the products, as I said, are pollutants, objectionable pollutant. This is where the objection for IC engines is coming in. So we do a lot of research on these products, okay, the pollutants that are emitted from IC engine combustion. So you need to track composition of the combustion product because they are pollutants. Some of them are pollutant. By applying thermodynamic principle, you can have an estimate of the composition of the combustion product. There are two approaches here. One is stoichiometry based approach, which provides you combustion product composition. Second approach is chemical equilibrium based approach. And this approach is based on first and second law of thermodynamics. Okay, first and second law of thermodynamics. Stoichiometry based approach is a simplified approach. It will give you only some minimal composition. Okay, you cannot get all the product information by applying stoichiometric principle. Only major species that are present in the combustion products can be obtained. Species information can be obtained by stoichiometric principle. More product information you can derive by applying chemical equilibrium. So these are the useful information I would say you can get by applying thermodynamic principle, and that is where it is useful. So you are going to get some parameters, important combustion parameters, which will help you to analyze a combustion event. So that is the reason why we start with a thermodynamic based approach, and then we will move on into actual combustion event. So we have just now discussed why we are studying thermodynamic based approach to start with. Okay, so the next topic I'm going to talk about is combustion stoichiometry. So when I say that we are talking about stoichiometry, stoichiometry refers to chemically correct proportion of fuel and air that we consider. Okay, and this is one of the principles that we use to get the composition of the combustion product, major combustion product, not all the product. As I said just now, you can get information about the composition of major combustion product by applying stoichiometric principle. So what does this stoichiometry means? The stoichiometry means it actually deals with minimum quantity of air required for the complete combustion of 1 mole or 1 gram of a fuel. Generally, chemical equations are written on molar basis, but engine analysis, combustion analysis is generally on mass basis. So we will start with the discussion on this principles on mole basis, and then I will say about how we can convert this mole into mass basis. Okay, so this stoichiometry is nothing but it's a minimum air required for the complete combustion. So note this word, complete combustion. This is the minimum air required for complete combustion of 1 mole or 1 gram of a fuel. Okay, and by applying stoichiometric principle, we are going to relate the composition of the combustion product with the reactants based on what? Based on the conservation of atom or mass in each element in the reactants and product. So you have a combustion phenomena happening with fuel and air, which are reactant, and that lead to various product. What we do here when we apply stoichiometric principle, we are going to get information about product composition by relating products with the reactants. How do we relate this to? Based on conservation of mass or conservation of atom, meaning that the atom in the reactants, total atoms in the reactant and total atom in the products are conserved. Similarly, total mass of each element in the reactant and product are conserved. So this is conservation of mass or conservation of atom principle that we apply to get information about the product composition, which is what we want to get. So here we deal with IC engine combustion. So meaning that the fuel we consider are gasoline and diesel, which are hydrocarbon fuel. In the first unit, we spent time to understand more about this gasoline and diesel. And we understood that they are hydrocarbon fuel primarily consisting of carbon and hydrogen. Carbon is around 84%. And then hydrogen is around 14%. The remaining 2% are trace elements. So the major elements or atoms present in gasoline and diesel are carbon and hydrogen. So here we are talking about complete combustion. So hydrogen will burn to H2O and carbon will burn to CO2 when we apply stoichiometric combustion equation. Okay, so we have two major elements and that will burn to CO2 and H2O. And we are combusting this hydrocarbon fuel with air, and what we have in the air, the two major composition or components in air, one is oxygen, 21% by volume, and there is nitrogen, which is 79% by volume. So in fact, nitrogen is 78. I have observed all the other trace element in nitrogen. Okay, so you will have argon, CO2 and other trace elements. I use the word trace element because their composition is very small. Okay, composition is very small. All those are absorbed in nitrogen. Okay, and that's why we are considering it as 79 and 21. 79% nitrogen and 21% oxygen. So this is what we have in air and what we have in gasoline and diesel, carbon and hydrogen. Now we are going to see how to write a stoichiometric combustion equation for hydrocarbon fuel. This is a general stoichiometric combustion equation which is applicable for any hydrocarbon fuel. Okay. And through this analysis, what we want to get information about the product composition. So I've written the equation with the general form C alpha H beta. What is alpha? Alpha stands for number of carbon atoms. Beta stands for number of hydrogen atom. C alpha H beta is a typical hydrocarbon fuel. It can be gasoline, it can be diesel, or it can be any hydrocarbon fuel. So this is combusting with air. Fuel is combusting with air. In air, we have oxygen and nitrogen. 1 mole of oxygen is accompanied with 3.76 moles of nitrogen. Can anyone tell me how I get this number 3.76?
Ratio, sir. 21 by 29 by 21.
Exactly. So 79 by 21 will give you this 3.76. Okay, meaning that with each mole of oxygen, there will be 3.76 moles of nitrogen. This is what is present in air. Since we are writing stoichiometric combustion equation, I am writing 1 mole of O2. That's why it is accompanied with 3.76 moles of nitrogen, and that is multiplied by A. A is a coefficient. You can call it as a stoichiometric coefficient. So fuel here is combusting with air, producing various products. Products are shown on the right hand side. Okay, so these are the combustion products. These are the reactants. Fuel and air are the reactants. And on the right hand side, we have products, 3 products, CO2, H2O, and N2. How do we get these 3 products? Carbon burns completely, producing CO2. Hydrogen burns completely, producing H2O. Nitrogen in the air is coming out as it is. So I have assumed that the nitrogen is not undergoing any reaction. This is a reasonable assumption because nitrogen is inert. It's a very stable molecule because of the presence of triple bond. Okay, it's inert, it's a lazy fellow. It won't participate in the chemical reaction quickly. If you have to make it to participate in the chemical reaction, you have to provide a very high activation energy. So this happens at a very high temperature, well above 1800 Kelvin or so. For writing stoichiometric equation, we assume that the temperatures are low and nitrogen comes out as it is. Okay, nitrogen comes out as it is. So we have these 3 species in the product, CO2, H2O, and N2. I have written them with coefficient B, C, and D, which stands for number of moles of CO2, H2O, and N2. This equation is written on mole basis. Now, as I said, we are interested in finding this B, C, and D, which gives you product composition. Now, to get this B, C, and D, what we are doing here, we are doing atom balance, the number of atoms of the reactants, a number of atoms in each element of the reactant and in each element of the product is conserved. So we can balance carbon atom in the reactant side and product side. If you do the carbon atom balance, you will see that on the left hand side you have alpha carbon atom. On the right hand side and the product you have B times carbon atom. So alpha is equal to B. Similarly, you can do hydrogen atom balance. On the left hand side you have beta. On the right hand side you have 2C. Okay, so we are just balancing the hydrogen atoms on the reactant side and product side. Similarly, by doing oxygen atom balance, you can write it as 2A is equal to 2B plus C. Or in other words, A is equal to B plus C by 2, or we know that alpha is B and beta is 2C. So B will be alpha plus beta by alpha plus beta by 4. Because C is equal to beta by 2. Here I have C by 2. So it is beta by 4, alpha plus beta by 4. That is what is this A. Okay, so by doing this, then I have one more element, nitrogen. By doing nitrogen atom balance, you can write it as 2A into 3.76. That is what I have on the left hand side for the reactants. On the right hand side for the product, I have 2 into D. Okay, this equation is based on nitrogen atom balance. So how many unknowns you have in this stoichiometric equation? How many unknowns you have?
6 unknowns.
6 unknowns. What are they?
So alpha, beta, A, B, C, D.
Okay, so you can ignore alpha and beta. Let us assume that you know the alpha value and beta value because fuel is known to you.
Then
So the unknowns are there? 4. So you have 4 unknown. How many equations you can form? How many equations you can form?
Sir, 4.
4 equations. So you have 4 unknowns and you can form 4 equations by doing atom balance for the reactants and products. So this can be solved to get this unknowns A, B, C and D. What I am interested, as I said earlier, I am interested to get the product composition, which is B, C and D. I want to know the number of moles of CO2, H2O and N2, which I can get by doing this atom balance. Okay. So stoichiometric principle allows me to find the product composition. In this case, there are 3 products, CO2, H2O and N2. It allows me to get the values of B, C and D by doing simple atom balance for the reactants and products. Since I know A, B, C and D, now I have written the equation, stoichiometric combustion equation with the known values of A, B, C and D. That's what I have written here, C alpha H beta plus alpha plus beta by 4, which is nothing but A multiplied by O2 plus 3.76 into alpha times CO2, alpha is B, beta by 2 H2O, beta by 2 is B, then alpha plus beta by 4 into 3.76 into this is your D. Okay, so I know the values A, B, C and D from atom balance. I have written the equation with those. So this equation is on molar basis, but when we do combustion analysis, we always we are interested to get mass based analysis. Okay, so what I have done here as the next step, I am finding the mass of air required for the complete combustion of 1 kg mass of the fuel. So this is mass of air by mass of fuel, and with the subscript ST. This ST stands for stoichiometric proportion. Stoichiometric proportion of air to fuel can be written as, this is mass based equation. So you can write it as Na into capital Ma. What is this Na? Number of moles of air. What is this capital Ma? Molar mass of air. Similarly, on the denominator, you have number of moles of fuel multiplied by molar mass of fuel. Can you tell me how I get this equation? Mass is equal to number of mole multiplied by molar mass.
PV equal nRT.
PV equal to nRT. So here I am writing mass in terms of mole and molar mass. How did I get this?
Sir, mass of 1 mole into we are means simple multiplication we are doing in number of moles available.
So you know
number of moles multiplied by mass of 1 mole.
Number of moles is given by mass by molar mass. This is the equation, fundamental equation. From this you can get mass. What is that? Yeah, so this is the fundamental equation. From this you are getting this. Okay, mass is equal to number of mole multiplied by molar mass or molecular weight. And for the air, you have a number of moles of air and molar mass of air. For the fuel, you have number of moles of fuel and molar mass of fuel. So this number of moles of air from the equation can be written as this Na, number of moles of air can be written as alpha plus beta by 4 multiplied by, here you have 1 mole of O2, 3.76 moles of nitrogen, 1 plus 3.76, 4.6. So you have alpha plus beta by 4 into 4.76, that is Na. This is total number of moles of air you have in the equation. That is multiplied by molar mass of air. Molar mass of air is 28.84. How did I get this magic number, 28.84?
Experimental value, sir, it is. Hence we know the we know the composition of air, and we know the molar mass of all the components. So
Yeah.
we know the molar mass.
Yeah, from this you will get. So just now I said that we are considering 21% of oxygen, 79% of nitrogen in air. This is what I have in air. So if you take a average, you know, molar mass of oxygen and nitrogen. If you take an average of that, you will get this number 28.84, which is the molar mass of air. The denominator, you have a number of moles of fuel. Here in the stoichiometric equation, it is 1 mole multiplied by molar mass of fuel. For that, you need to know the atoms, number of carbon atom, alpha, multiplied by molar mass of 1 carbon atom, which is 12. Number of moles of hydrogen atom multiplied by 1, multiplied by molar mass of hydrogen, which is 1. Okay. So, so here you have this molar mass of fuel, and number of moles are 1 in the stoichiometric equation. So from this, so you know all these values. From this, you will get stoichiometric air mass that you need for burning 1 kg mass of a fuel. So now to get the values, what you fundamentally need is alpha and beta. Once you know alpha and beta, you are done. You will be able to write this equation. But finding alpha and beta for a multi-component fuel like gasoline and diesel are not straightforward. This is what we have seen in chapter 1. Gasoline and diesel are complex multi-component hydrocarbon mixtures. So they consist of around 1,000 different hydrocarbons, as we discussed in the first chapter. They are complex mixture. So how do we go about it? How do we get alpha and beta? You have to do some approximation here. This approximation is referred to as surrogate modeling approximation or approach. So what we generally do is the hydrocarbon class information of gasoline and diesel is known to you. This already we have discussed in the first chapter. So this is a hydrocarbon class information. Hydrocarbon class information for this is for gasoline and this is for diesel. So this information is known to you. What you do is you take once you know this hydrocarbon class information for gasoline, you take 1 or 2 representative hydrocarbon for each class, right, to capture the effect of gasoline fuel. So this approach is called surrogate modeling approach. We are going to choose only few hydrocarbons in each class. Okay, from that you will be able to get the molecular formula for gasoline or diesel that you need here in the combustion equation. Once you have that, you will get alpha and beta. Once you have alpha and beta, the entire equation can be written. You could see that the entire equation is written in terms of alpha and beta, only these 2 values. Okay, so we do this surrogate modeling approach. It's an approximation wherein we choose few hydrocarbon to mimic or capture the characteristic of the gasoline or diesel. So once you know this, you know alpha and beta. Once this is known, you will be able to write the combustion equation. Okay. And so what you need to know here is for complete combustion, you need around 14 to 15 kilogram of air for complete combustion of 1 kilogram of fuel. To burn 1 kg of fuel, gasoline or diesel fuel, you need around 14 to 15 kilogram of air. This is what you derive based on this stoichiometric analysis. And this information, I would say, is an important or critical information when you design the engine, because you need to fix the capacity of the engine, right? Volume, displacement volume of the engine. So this capacity can be fixed once you know how much of air is required to burn a given mass of fuel. This is what you are getting here. Although it is a theoretically correct proportion, this is an important information that you need to have. How much of fuel that you are going to burn in the engine is based on the rated power of the engine. Rated power of the engine will help you to fix the quantity, fuel quantity. Once you know the fuel quantity, you can fix the air quantity. Based on that, you can fix the displacement volume, VD, for the engine, okay, which is fundamental design information that you need to have. So this stoichiometric analysis helps you to fix the capacity, engine capacity, based on the rated power output that you need for the engine, okay. So we know that in an actual combustion event, air mass above or below stoichiometric proportion is used. We don't always use stoichiometric proportion of fuel and air, which is a theoretically correct proportion of fuel and air, right? We always use either higher value than stoichiometry or lower value than stoichiometric. So to deal with the actual requirement of using higher or lower air mass, this fuel air equivalence ratio is introduced to deal with the situation wherein we use either higher air mass or lower air mass than the stoichiometric proportion. What is this fuel air equivalence ratio? This is the definition for fuel air equivalence ratio. You could see that this is defined based on actual fuel mass to air mass divided by stoichiometric proportion of fuel mass to air mass. This is one way of defining equivalence ratio. The other way of defining equivalence ratio is presented here. Air mass to fuel mass based on stoichiometric proportion, air mass to fuel mass based on actual proportion. These two are same. I have written in different forms. That is it. Okay, so the equation is same. They are written in different form. Either they can be written with the fuel in the numerator or air in the numerator. Okay, when you write fuel in the numerator, it is actual fuel to air mass to stoichiometric fuel to air mass. Otherwise, if you write air in the numerator, it will be stoichiometric proportion of air mass to fuel mass with respect to actual air mass to fuel mass. That is how this equivalence ratio is defined. Basically, it captures the effect of using higher air mass or lower air mass than the than the stoichiometric proportion. Now, with this definition of equivalence ratio phi, there are three possible conditions. Okay, one is phi equal to 1, which is called stoichiometric condition. With stoichiometric condition, the major combustion products are CO2, H2O, and nitrogen. Again, I'm assuming that nitrogen is not oxidizing because of lower temperature. It's an assumption. And these three are the major species. Apart from this, there are other different species that the engine will emit as a resultant of combustion. Here, these three are the major products. The other condition is phi greater than 1. When phi greater than 1, what it implies? When phi is greater than 1, actual fuel mass to air mass is greater compared to stoichiometric fuel mass to air mass, meaning I'm using more fuel than the chemically correct proportion. So this condition is referred to as fuel rich condition. When phi is greater than 1, it is referred to as fuel rich condition or fuel rich combustion. When you allow engine to undergo fuel rich combustion, these are the major combustion products. You will have CO2, H2O, and N2. Apart from this, you will have CO and H2 as a major species. The CO is a product of incomplete combustion. So when you have a fuel rich combustion, it means that you have less air. Because of less air, you will have incomplete products like CO and H2 in larger proportion in the exhaust. Okay, in the engine exhaust. So this will be the product composition in case of fuel rich combustion. The third situation is phi less than 1. When phi less than 1, what it means, you are using less fuel mass to air mass. That is the actual case compared to stoichiometric proportion of fuel to air mass. You are using less fuel than the stoichiometric correct proportion. This you can call it as fuel lean condition or fuel lean combustion. You are using less fuel than stoichiometric proportion. That's why it is referred to as fuel lean combustion. If you have a fuel lean combustion, these are the products you can expect. These are the major products that you can expect in the engine exhaust. CO2, H2O, N2. Apart from this, you will have oxygen in the product. Because it's a lean combustion, you are using more air than what is theoretically required. Because of using more air, this excess air will appear in the product, exhaust product. So these three are the possible situations encountered by the engine, okay, in actual situation when you run a SI engine or CI engine. All these three possible conditions are happening, okay, either stoichiometric or fuel rich or fuel lean combustion is happening both in SI engine as well as in a CI engine. Now, when you look at the SI engine operating condition, the phi value will be in a closer range of 0.9 to 1.1. This is true for any kind of SI engine. It will be smaller or larger SI engine. This is the operating phi range for spark ignited engine, irrespective of the engine size, 0.9 to 1.1. So you see that you are running close to stoichiometric condition. SI engines are run close to stoichiometric condition most of the time. Later on, when we discuss in detail about the combustion event, you will understand why we run SI engine with such a close phi range and that too closer to stoichiometric condition. One of the major reason is you can maintain a stable flame only if you run engine under this fee range. SI engine combustion is a flame propagation based combustion. Just now I discussed. To maintain a stable flame, your fee should be closer to stoichiometric value. Otherwise, it's very difficult to maintain a stable flame. And other one, three-way catalytic converter is most commonly used. And this converter efficiency is high only if you run the engine close to stoichiometry. Later on, we will see why it is high under stoichiometric proportion, okay, of operating fee. But here, just take a note that because of these two constraints, flame stability is better under stoichiometric condition. Catalytic converter efficiency is very high under stoichiometric condition. Because of these two reasons, you run SI engine close to stoichiometric. This is a very close margin of fee that we use for SI engine. CI engine operating condition, the fee value is around 0.4 to 0.8, meaning it is less than 1. So that is why it is called lean combustion, fuel lean combustion. Okay, most of the time you run fuel lean combustion, you use up to 30 to 50% XSR. That's why engine size is always higher. Diesel engine capacity or VD, displacement volume, is always high compared to SI engine because we use up to 50% XSR. One of the reason is this fee value, although overall value is lean, you have heterogeneous combustion in a CI engine. This heterogeneous combustion leads to locally rich mixture. That is what is causing particulate emission. You have particulate emission problem only in diesel engine, not in SI engine, because SI engines undergo homogeneous combustion. Here, CI engines undergo heterogeneous combustion. That's why overall mixture, this is called overall equivalence ratio, that is maintained very lean with around 50% XSR to avoid high particulate formation. Okay. There is something called XSR ratio lambda, which is a reciprocal of phi. Lambda is equal to 1 upon phi. We generally, I prefer to use phi rather than lambda, but in some of the combustion analysis, people also use lambda. That's why I have given here, which is nothing but reciprocal of phi. It's time up. I stop here. If you have any questions, you can ask me. Are there any questions?
Yes, sir. Just a minute.
Sir, like you mentioned, it is very difficult to difficult to analyze the flame propagation and this combustion behavior. So in case of any issue, like if we are in development stage of new engine and we see any issue, like, or we are not able to achieve the estimated power or these kind of performance issues, if we are predicting, how do we resolve it? Like, what is the approach to go with, sir?
No approach, we don't have any major problem, fortunately, because combustion as such is complex on a microscopic approach. Microscopic approach is based on the kinetics approach. Just now I said that the kinetics are based on chemical reaction pathway of hydrocarbon, and how many hydrocarbon we have in gasoline and diesel, it can go up to 1,000. And each of these hydrocarbons has a characteristic reaction pathway. You understand the complexity. So whatever you see as a pressure change or temperature change in the engine cylinder is a resultant of, or is the contribution of, energy release from each of the hydrocarbon, which have their own characteristic reaction pathway. So on a microscopic scale, it is very complex. It is difficult to understand. But how do we go about in designing a new engine? We generally follow macroscopic approach. We deal with gross parameters like total energy release, how the pressure changes. You have a pressure sensor, you measure the pressure in cylinder pressure. That is how you do engine development. Engine development now is done primarily with a macroscopic scale based parameter, not microscopic scale. At the microscopic level, still it is not understood. This is what I am highlighting here.
Understood, sir. Thank you so much, sir. Sir, one more doubt, sir. Like we have a variation of almost 10% in all the parameters, which is acceptable in comparison with idle fuel, like the tolerance zone we say. So there is a possibility, just my understanding, sir, there is a possibility that same vehicle can perform 10% better or can have 10% better mileage in with particular batch of fuel and 10% less mileage with particular batch of fuel, sir. Means-
Exactly. So whatever you do is optimization. Optimization is a compromise between two effects, right? When you do optimize, you are actually minimizing the trade-off. In engine, always there is a trade-off. There is a positive effect, there is a negative effect. When you talk about better fuel economy, is a final outcome of minimum trade-off between positive and negative effect. Always there is a scope to improve further. So as you rightly said, there is always we do this optimization and close at some point of time because of want of time, right? If you keep on optimizing further, there is still scope. That is the beauty of engine research, right? You always have a scope to improve something. That is how we do research for more than 100 years, right? Always there is a scope to explore something new.
Yes, understood. Thank you so much.
Okay, thank you.
Sir, one question from my side for yesterday's class.
Yeah.
Sir, regarding the fuel specification. So my question is like within the fuel specification, whether the oil companies vary the limits, say the volatility based on the zones in India, like cold region they'll give higher volatile fuel, or hot engines they'll give with better on something like that, like, or within
no, it is not region. It is not region based. Northeast or northern region, they may not have different specifications, but it is based on the season. For summer and winter, the temperature values are significantly different. Based on seasonal changes, there are some variation, but not based on region. So how it is generally approached is in Northeast, where you have a very cold weather surrounding ambient condition, you may have to use some additive to comply with the standard. Otherwise, it's not possible to run the engine.
Okay, sir. Thank you.
Yeah, thank you.
Sir, in that equation, when we had told 28.84, similar to that 4.76, how did we get?
4.76 is 1 plus 3.76. 1 mole of oxygen plus 3.76 moles of nitrogen, that is 4.76 moles of air, multiplied by alpha plus beta by 4, which is a coefficient.
Okay, sorry, my bad.
Yeah. Okay, fine. So I stop here. I will see you on Monday. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Nice week ahead, sir.